والphase motion. هلا last time what we showed for this example, we showed that the zero limit, okay, that the zero limit was around here, okay, and we showed that now that any 20 log 1 over beta which comes above the circuit, this line leads to proper behavior and a good gain margin, and any beta that comes below it will lead to an unstable design. Okay, so if my reference circuit line of the 20 log 1 over beta is here, okay, this is my reference or zero limit, and if I get the 20 log 1 over beta to be here, then this is really an unstable design لأنه أنا عندي إياها أوطى من zero, it's below the zero limit. So for this unstable design, what we want is we want to stabilize it, and there is a rule of thumb that says that if I have any A behave form, يعني any a certain transfer function with 20 log A, if the 20 log 1 over beta line intersects where the slope is 20 minus 20 dBs per decade, then the system, as a rule of thumb, should be stable. لأنه if the poles are relatively spaced out, يعني if I don't have too many clustered poles, okay, this means that at most at this point, okay, I have from the first pole minus 45 degrees, and from the other poles maybe يعني how much they could give. If they were two, they could give me minus 90 if they happen to be very close. So I am still safe. I still have the intersection is still happening before the omega 180. يعني عملوها مثل rule of thumb إنه if the circuit is designed well, the phase contribution إذا أنا عملت intersection هون definitely would be less than minus 180. So if we believe this, and you will see an example that might hint to it later, then my objective is to stabilize this circuit. So given a circuit that has three poles, one at 10 to the 5, one at 10 to the 6, and one at 10 to the 7, and that has a 20 log 1 over beta line already at 40 dBs, I need to modify my design either by introducing a new pole, okay, or shifting the first pole so that what happens is that this line instead, يعني أنا عندي هون disjoint point, here I have another disjoint point, so that this line really intersect at a slope which is minus 20 dBs per decade. Now it is not. Okay, طب. Great. So let us see what we can do. So this is my first pole, and here I'm going to introduce a new pole. If I introduce a new pole P0, then my new system will really have P1 prime, P2 prime, P3 prime, and P4 prime. So what happens in this new system when I introduce a new pole? Okay, my P1 is now the second pole, and the new pole that I am introducing is the first pole. Okay, so let us see. I don't want to keep pushing the pole very, very far backward, because if I push it very far backward, the bandwidth will die. But I know that if this is my first pole, when I hit it, what is the slope? Minus 20 dBs per decade until when? Until I hit my second pole. Okay, my second pole is my old first pole, right? So if I design my system such that I add the new pole such that when I reach to my second pole, I would have reached to this 20 log 1 over beta. يعني إذا أنا بطلب, if I request that, okay, the intersection happens at my old first pole, then this means I am requesting that at this point I have P1 and I have 40 dBs. Okay, okay. Then what is this? Where يعني شو بكون what did I guarantee؟ بكون أنا I satisfied the requirement of minus 20 dBs per decade. Okay. And I satisfied the requirement that the 20 log 1 over beta line intersects with my new transfer function at what point? At minus 20 dB, at a slope of minus 20 dBs per decade. هيك لنرجع نشوف شو صار. طيب. So,
Professor?
Yes.
I have a couple of questions. The first one is it should intersect at a point where it changes the slope or bus at minus 20 dBs per decade.
It can intersect anywhere in here. يعني خلينا ناخدها على old circuit. لو أنا عندي old circuit, what does the rule of thumb say? It says I can accept 20 log 1 over beta to be here. I can accept it to be here, and I can even accept it to be at this point, صح?
Yeah.
Okay. So if we inspect the old system, in the old system, this is P1, this is P2, and in the worst case, I can have my 20 log 1 over beta passes through this point, right? So if I have this value and I have P2 and I know the low frequency gain, I can find P1 from it, right? So, if somebody gave you P2 and they gave you the value of 20 log 1 over beta, وقال لك it intersects it at that value, and we gave you the slope and we gave you the 20 log AM, would you be able to solve for P1? If I didn't give it to you, assume you don't have it, but you have P2. Yeah. Right? So if I tell you that I have a 20 log 1 over beta which intersects here and it happens at a frequency 10 to the 6 and its value, right? And you don't know this, and I tell you this is 100 dBs, right? And I tell you find for me P1, you can solve for it, right? So what we are doing here is we are saying, since I have to live with the 20 log 1 over beta equal to 40 dBs, okay? And I know this is P1, P2, P3. I'm going to introduce a pole P0, okay? اللي هي بالنسبة لي P1 prime بالnew system, and this becomes my P2 prime. And I'm going to force that the system will somehow have a minus 20 dB gain, okay, all until P2 prime, or all until my old first pole, but such that the value at the old first pole هو P1, right, and 40 dB. يعني أنا بدي أجبره, I want to force it, and in this new system, okay, the body plot will have a value or intersect the 20 log 1 over beta, okay, at P1 لحتى يكون عندي هون minus 20 dBs per decade. Okay, يعني I want to force it إنه يكون في عندي drop, okay, by 60 dBs at P1, and the point P1 هي تكون على conjunction of the intersection of the minus 20 dB line and the 20 log 1 over beta line. وضحت هاي the requirement?
Yeah.
Okay, so أنا فعلياً بدي يكون على 10 to the 5 equal to 40 dBs. Okay, I know at P0 it is 100 dBs. I can now solve for it. Okay, that's it. So هلا بنصير نقول G2 equals G1 minus 20 log omega 2 على omega 1. Okay, and now we can say, well, G2 is 40 equal to 100 minus 20 log P2 is my 10 to the 5, and P1 is the P0 I am solving for, and we can find what it is. Okay, so هاي بتصير minus 60. عندنا 3 تطلع أصغر منها 10 to the 3 تطلع 10 to the 2 تطلع here. Okay, so anybody has a question about this?
Can we add a 0 instead of a pole at some point? Or is it easier to add a pole than adding a 0?
Zeros are typically not desirable لأنه they have a slope going up.
Yeah.
Right?
Yeah, I was asking so,
and if they are negative zeros, maybe they are difficult to obtain in the circuit, and if they are negative zeros, they will add to the phase. And I'm not sure how positive zeros are realized. So typically, poles are the easiest because they guarantee the phase. Okay, يعني أنا at minus 20 dB with a single pole بتكون أول pole عطتني contribution 45 degrees, and the second pole بتكون already صارت عطتني minus 90 عفوا. The first pole, pardon me, maybe I said it wrong in the beginning of the lecture. إذا في عندي 10 folds أو أكتر، يعني هون بهالإكزامبل الفيرست pole قد إيه بتكون عطتني؟ هون قطعنا 10 folds صح؟ So the first pole gave me 90 degrees fully, and the second pole would have given me 45 degrees صح? From the second pole, right?
Yeah.
And so this is minus 135. Hoping that the other poles are far, and they have not started to contribute yet, as is the example here. Okay.
All right. Thank you.
Okay. So this is why it matters for us the phase, and therefore, فإذا بالنيو pole the rule is simple. بس حنحط P1 يعني 10 to the 5 40, and this will be P0 100, and we will solve for P0 and we know the slope. Okay. طب هلا if we have another method, the other method says, well, what if I shift the first pole? if I shift the first pole, يعني أنا if I shift the first pole أنا كان عندي P1 P2 P3, so this will always be my second pole, and my second pole is always my reference. Whenever I hit it, I will switch the slope, right? Okay, so if this is my second pole, and let us say I move, so first here is my inflection. Now if I move this here, this will be my inflection point, right? And if I move this further, P1 further to this point, then this will be my inflection point. Okay, so as I am moving P1 to the left, I'm shifting it, I am making the delta or the drop by the time I hit P2 larger, until it is large enough such that the intersection of the minus 20 dB per decade line and when I hit P2 happens at what point? At my 20 log 1 over beta line. Okay, يعني I keep pulling P1 to the left until really the inflection point محل ما بده يتغير السلوب happens at 40 dB على 20 log 1 over beta line. Okay, so to achieve this requirement or desired requirement really إذا هيدا البول 2, okay, I find it's the intersection إنه إذا أنا بدي this point to be pole 2 اللي هي 10 to the 6 and 40 اللي هي فعليا P2 and 20 log 1 over beta in general, right? P2 and 20 log 1 over beta. Okay, this is the first point that I have here. And then the second point, what is the second point? هيدي point 1 اللي هي هون A. Okay, and point B, well, what is point B? Okay, I'm moving P1, so this is P2. I'm moving P1 backward to a point or to a frequency, okay, to obtain this. So this point qualifies as P1 prime. And what is the magnitude here? It is 100 dB. So this is my point. إذا هي سميناها B. Okay. This is my point A. Okay. And it is P1, which I don't know what it is, and 100 dBs, which is the low frequency gain. Okay, so P2, I know it, it is 10 to the 6th, right? And 20 log 1 over beta, I know it. And I know the low frequency gain, so I need to find what P1 is. Is this clear? Okay, so عندنا two methods. These two methods either add a new pole, okay, and in that scenario my old P1 becomes P2 prime, and this is P1 prime, and this is 20 log beta or the 40 dB, وهيدي هي low frequency gain. In the other scenario, I'm going to shift the first pole. So in this scenario, really, I will have always my second pole as my P2 prime, and P1 prime will be the unknown because I'm shifting the first. Okay, so هاي بيكون عندي 10 to the 6, 40 dBs and 100 dBs and the question mark. Okay, now what is the difference between these two? The difference is as follows. When I shift the first pole, I have a wider bandwidth, and I am not dropping to low dB fast. Okay, when I shift the first pole, I am not dropping to low dB fast. Okay. Whereas when I introduce a new pole, I am dropping faster because this becomes my second pole. Okay, ففي trade-off here, but really it depends what are the implementation methods and the circuit methods. Okay, but great. So this is what happens, and this way we can push the 20 log 1 over beta to intersect at the edge of minus 20 dBs per decade. How do I shift a pole? If I have a circuit where I have an RC time constant, صح هي الأوميجا equal 1 over Rx times Cx. If I want to make it smaller, يعني مثل قبل we went down from 10 to the 5 to 10 to the 2 for P1, right? So what do? I need to add another compensation capacitor. Okay, so that this part of the circuit will have a different pole. Okay, let's say it comes from the input circuit. So we're going to add a compensation capacitor. Now, the problem with this compensation capacitor إنه أنا كان عندي 1 over 2 pi Rx Cx هي تعطيني 10 to the 5. Now I wanted to give me 10 to the 2. So what order of increase CC has to add? يعني how much larger than Cx? يعني Cx plus Cc have to become what quantity? قد ايه بده يكبروا؟ Twice, thrice, or 1,000 times?
1,000.
1,000 times صح؟ ما أنا كنت بدي يعني إذا عندي 1 على A هي 10 to the 5 بدي يصير حط 1 على 1000 A لتصير تقريبا 10 to the 2, right? So that's a lot. I will need a really huge capacitor. So what is a good way to get a big capacitor with some multiplicative effect without having to worry about making it large? مين الكاباسيتنس اللي كان ينضرب بجين 1 minus K وهيدا which capacitor? 1 minus 1 over K on the other side.
CU, I think.
Exactly, Miller يعني, right? So we rely on Miller. Okay, so we rely on Miller capacitance in order to get the multiplicative effect. Here we are not showing a transistor. We're showing more like two stages. If you recall the first circuit that we studied, or when we studied the gain of the differential amplifier, we said we can summarize it into two circuits. What happens is if I put a feedback or some compensation capacitor CF here, it will result if I solve the big system in 2 poles and 0. And if we solve the big system, what we are going to find is we are going to find the first pole we really have CF multiplied by the RXY, and therefore it will have CF times R2 times the gain. Okay, and therefore this way I can get a large compensation, يعني a large shift in my first pole, whereas the others are not subject, as we find from the complex equations here. Okay, so this is what typically they follow. Okay, so Miller compensation shifts the dominant pole to the left. Okay, while it shifts the other poles to the right, and he تضرب 1 over the gain, right? Also, the compensating capacitor is multiplied by GMR2, and this allows to use much smaller capacitors on the chip. Yani we don't need to have large capacitors on the chip. Let us look at here. This is an example to the complex numerical equations that we have there. We start with FP1 equals 3.2. We end up with it being 0.3 megahertz. Okay, in this case, it shrunk by 10x. And where the coupling capacitor is 0.2 picofarad. Okay. And then for the FP2, it was 10, it becomes 57, and we have a 0 at 800 megahertz. The 0 is very far. Okay, so هلا عم نمر على high level and هون numerically involved. يعني the objective is just to demonstrate the concept in this application. So let us look at this circuit. This circuit is the differential, the op-amp. Remember, we said it is a differential amplifier, and that we put a common source stage after it. We place this coupling capacitor between the two stages, and this is the first input to output, and this is the second stage from here to here, right? We put a coupling capacitor between the input and output of the two stages. If we go back up, if you look at this circuit, this is the first stage, and the second stage relies on it, and this is the output of the second stage. Okay, great. Hala, what I really care for from this complex drawing is that, you know, for example, I said, so this is V plus and V minus, this is the op-amp, this is the V minus, and this is the P plus. I have a feedback from the minus terminal to where? To the output. Yani I have a feedback from the minus terminal to the output. And this is a non-inverting amplifier, right? And 1 plus R2 على R1, right? And we explained that the feedback beta comprises of 1 plus R2 على R1. Here R2 is 0 and R1 is infinity. ما في عندي circuit is not like this, right? And this is what? This is a unity. This is a voltage follower. But from inspecting the feedback, what is the feedback? يعني إذا أنا هيدا unity، شو الفيدباك؟ أنا إذا عندي feedback هيك، هيدا VO هيدا VF. What is VF equal to? شو البيتا ratio? Exactly. So beta is equal to what? 1, right? لأنه VF equals to VO. فإذا يا أما in this configuration you recollect that if you have R2 over R1, right? يعني if we go back to the old circuit, we said that the beta هي هيدا circuit, and and you set R2 to 0 and R1 to infinity. يا أما you observe it by inspection. We know that this is a follower. And the feedback that I am sending is VF equals to VO, and the feedback network is like this. Okay, great. So هلا بلشنا نعرف إنه أنا I can design circuits if beta is equal to 1, and you'll see many final exam questions where we tell you assume beta equal to 1, or with unity gain feedback, يعني beta is equal to 1. What is 20 log 1 over beta? 0. Okay, so high 0. Great, excellent. So this circuit has now 20 log 1 over beta equal to 0. So Anna, if I give you a problem, the transfer characteristics, if the transfer characteristics of 20 log A are provided for you, and you know that it has a unity feedback gain, يعني 20 log 1 over beta equals what? equals 0 صح؟ So the intersection point between the two, omega 1, happens to be in this specific scenario, in here only, لأنه 20 log 1 over beta equals 0 هي لما is equivalent when the A transfer function becomes 0 dB and it is equal to the unity gain frequency in this specific scenario اللي هي ft. And we know that ft, let me mute your friends 1 second if you're getting noisy. Okay. And we know that ft is equal to what? Is equal to f3 dB times am. يعني these are the little tricks that you might see. Okay? So, for example, if I give you fp1 and fp2 and fz already, okay? And you know the am, so you know the 20 log am, okay, a low gain, a low frequency gain, okay? You can derive ft from it because you multiply this quantity, you need am, pardon me. You know am, right? Or okay, from the transfer function. And so you can multiply am by the 3 dB frequency and you can get the ft, okay? طيب, great. Now, what do we want? In this specific design, they require that ft be smaller than fp2 and fz, okay, so that it remains in the minus 20 dBs per decade. Okay, let us look at this example. بس هيك نعمل inspection at the contribution of the نرجع له. Let me look at the equation and ask a couple of questions. The 0 that they showed me here, is it positive or negative? في عندي minus sign here, right? So this means that the 0 is going to contribute minus 90 degrees. And I have two poles, each one of them will contribute minus 90 degrees, صح? So what is happening here is I want to guarantee that when I intersect the 0 dB or the 20 log 1 beta in this example, that this omega 1, which happens to be equal to omega t, happens before fp2 and happens before fz. Okay, and I want it to happen basically in the minus 20 dBs per decade before I get to see strong contribution from the other phases of the other pole and 0, the remaining ones. Okay, so so in order to achieve this, what we see here is that given fp1, fp2 and fz, and knowing what am is, اللي هي كانت am is equal to gm2r2 times gm1r1, if it is given, okay, I will find that ft is equal to gm1 over 2 pi cc, and now I can put a condition to compare ft to fp2 and fz and find the criteria. Our criteria is that I want gm1 to be smaller than gm2, and the other criteria is that I want cc over gm1 to be greater than c2 over gm2. يعني هذه صارت بس pure math، إنه عم حط الإيكويشن ل ft اللي هي gm1 على 2 pi cc. I'm requiring that it be smaller than fz, for example, which is gm2 على 2 pi cc, and I can cancel this and get this required. Okay, but the most important thing here is that you know if beta equal 1, 20 log 1 over beta is 0, and therefore I will be inspecting the intersection of the 20 log A curve with 0 dB line, and therefore I can find omega 1 from omega t in this scenario. This is very important. Okay, anybody has any question? The big picture clear, the beta equal 1 feedback clear? Okay.
Yes, clear.
Okay, thank you. Great. طب هيدي it concludes stability, it concludes the analog design, and this is the most complex thing. Pole shifting, new pole, and the relation of the intersection of 20 log A with the feedback loop. هلا we're going to move to part 8. Part 8 and 9 are basically repetition with a slight advancement to what you have learned in 310 about the inverter. Okay, they are very important because it's quite a new topic, but typically, as you see in the previous finals, there is a good amount of questions on these parts, and 6-7 questions typically, and they are easy if you just get the concept. Okay, and okay, you will see that the questions are of the same family type. Noise margin, VOH calculated, VOL, the sizes of the transistors, the number of transistors later when we study the logic gates briefly in the part 9. Okay, so let's focus on this new part. So we're going to talk about digital electronics. Okay, so the analog electronics, what it does, and typically in a chain, I receive the signal. Okay, I amplify it. Okay, process it, amplify it, or process it to send it, amplify it, and stuff like that. And later I will have an analog to digital converter. Then I will store it. It's very much easier to store data as binary. Okay, and I will perform digital signal processing on it. And of course, I can have it in the RAM, I can have mathematical functions on it, etc. And then if I want to send it back, I will use an analog to digital converter, and then, okay, transmitter, and so on and so forth. Okay, so that's why digital design, it's always easier to operate in binary. It is efficient to store in bits. And therefore, since we have binary nature, okay, then we need to design logic gates or logic circuits that can operate on this binary type of signals. Okay, logic inverter is the basic gate which you have seen before in the 310. If I have input 0, output is 1. Basically, if I put an output low, I will get an output high, and if I input an output high, I will get an output that is low. Okay, so it is an inverter block. The simple transistor implementation of the inverter, there are many versions, but the simplest is a transistor and a resistor. This is an NMOS or a pull down, okay, that turns on or off as function of Vn. Okay, the resistor is a load device, and this load device basically connects the output to VDD. So if this device is off, it pulls the output up to VDD, and if this device is on, then those two form some form of a voltage divider circuit that is hopefully, if the R on is small, going to pull down the output closer to ground. Okay, and this RD has to be typically larger than the effective on resistance of the pull-down device. لأنه ideally, if this is an ideal switch with no resistance, it's going to pull down the output to 0. Okay? طيب, great. هلا, we have a single supply. Let's look at the DC characteristics of this curve. Okay? Great. We always put a table, a little table, and this little table for each device. So I have the NMOS. For the NMOS, now we have to remember a little bit the current equations. The current equations are simple. Let us write them here on this side. I have three regions. First region, if Vn is less than Vt, the device is off and I is equal to 0. This is if VGS is less than Vt, right? The second two regions qualify when VGS is greater than Vt. Okay, so this is when VGS is greater than Vt, and when if VGS is larger than, if VGS is small, if VGS, let us compare VOV, pardon me. So I have the quantity VGS minus VT. Okay, so if the quantity VGS minus VT, which we qualify as VOV, is small and VDS is large, okay, if VDS is large, then I am in the saturation region. I'm not putting them in the same order. Then if VGS minus VT is greater than VDS, and of course VGS is greater than VT, okay, then I will have the circuit in the linear, the transistor in the linear region. Okay, طب خلينا let me insert here بس one slide to refresh you for the different types of devices, PMOS and NMOS. Okay, so let us just to have it as a refresher, quick refresher slide. Okay, so this is for what device? This is for the NMOS, right? So this is for the NMOS device. In this event, the current here is equal to half K prime W by L VOV square or VGS minus VT all squared. And in this case, the current is equal to K prime W by L times VGS minus VT times VDS minus VDS squared over 2. You can remember it this way, or you can put a half outside. I don't know, I think you remember it by putting a half outside and multiplying the first entry by 2, right? That's how you remember it, right? Okay. Okay, so those equations, you need to have them always handy. Hello. Let us look at the rule of thumb. The rule of thumb says if I have my transistor, if it is an NMOS, for region 2, okay, typically this delta, if VDS is large and VOV or VGS is small, then I am really operating in the large VDS, so I am in saturation. Okay. On the other hand, if I have my transistor and if VOV is large and VDS is small, okay, then I am operating in the small VDS region for the specific relation, yani, and I am in the linear region. So this is a rule of thumb, but we typically compare those two values, okay? If the VDS is much larger, I'm in sat. If the VDS is much smaller, I am in the linear region. Okay? So let us clear. Okay. Let us now look at the PMOS device. The PMOS device, what happens there? So for the PMOS device, in the context of the inverter problem, typically, since the source node is connected to VDD, okay, the higher voltage will be the S, this will be the gate, and then the drain will be here. And then I can have a resistor, or I can have another NMOS transistor, or stuff like that to perform the inversion, okay? So for the PMOS device, if this is my S, I'm drawing it opposite just for you to be comfortable with the notion VSG, and this is how typically it appears in the circuits. Okay, so if this is my S, then what we do is we study VSG, VSD, and absolute value of VT, P. Okay, and we apply the same equations. Now, the idea, let us assume that I have an inverter, which is the NMOS, the CMOS inverter, pardon me. And if this is the output, okay, the way I study it, I try to inspect if VSD is large, and if V out is small compared to VDD, okay, and if VSG is small, then I am in the saturation region. Okay, so if VSD is much larger than VSG minus magnitude of VT, then I am in sat, else I am in near. Okay, is this clear? Okay, so now we can head back to the inverter DC characteristics and inspect this curve here. For the inverter, let us put a table for the transistor. We're going to say I have my NMOS, this is an NMOS, so I want to find VGS minus VT quantity, and I want to find VDS quantity, and I want to determine the region. Always do that. Now here, what happens to be is that VGS is equal to Vn. Okay, so this is really Vn minus Vt. And VDS is really equal to what? This is the drain. It is equal to V out. Okay, so let us inspect. When Vn is less than Vt, it's like VGS less than Vt. So the device is off. Okay, so the transistor is off. Okay. The next region, what happens as I increase Vn to slightly above Vt, the device starts to turn on. It starts to pull down the output slightly. يعني بعد output large. This is an inverter. I need to put effort. As I increase VGS, Vn, I start to pull it down. When the output is still large, okay, so if the output is still large, and the input overdrive VGS minus VT or Vn minus VT is small, then what region I am in? This is greater, and therefore I am in the saturation region. Okay, until Vn becomes very large. So when Vn becomes very large, okay, when Vn becomes very large, then in this scenario, when Vn becomes very large here, okay, then I have a very large input and a very small output. And in this case, this is my VOV, this is my VDS. I know that this is small and VO equals VDS in this context, and this is Vn minus Vt, and this is very large now. So this is greater, so I am in the linear region. Okay, فإذا when the device acts in its normal function اللي هو pull down, when it pulls down things, when the Vn is large and it has strong pull down capability, I would be in the linear region. Okay, we'll clear the three regions. Okay, great. So now I have this transfer function. I can approximate it by a simple form where instead of having the response like this, I know that for low input, I will have a high output. So this would be my VOH. So if this is my inverter, if my input is low, my output is high and I get VOH. And then if my input is high, my output is low and I get VOL. So this level is VOL here, and this level here is VOH. So I know the output is going to fluctuate between VOH and VOL. Now, if I have a second stage, if the input is VOL, the output will be what? VOH. And if the input is VOH, then its output is going to be VOI. Yani, putting this here are just reflecting that inside the circuit, if one pin or one output is fluctuating between VOL and VOH, then the rest of the circuit will receive input signals in this range. Okay, فإذا these are determined as outputs, but they will propagate inside the circuit as inputs. Okay, طيب great. Hello, let's look. So this is my logic 0, this is my logic 1, and this is my logic input 0 and 1 that will propagate in the design. Okay, so let us now see what can happen in real life. So while my input signal as function of time can fluctuate between VOL and VOH, in real life, I may get input signals that are noisy, and usually noise that adds up to them. Okay, so I want to determine where the circuit can operate and still provide me the logic 0 and logic 1. Okay, so let us see. If the noise increases the voltage at the input from VOL to V1, and let me assume that this is V1. For this specific amplifier, I will still get an output that is what? That is VOH, right? So this is noisy VN and this is V out. I will still get a VOH. Okay. However, if the noise is so large that it exceeds this range, the safe range, then I will start to get a low output and I will be in the risk zone. So this is why we define a noise margin. Okay, this is why we define a noise margin, okay, to guarantee that my output is still sufficiently high. This is the margin within which I can operate. If I operate beyond that, the circuit will fail. Okay, so let us see then, okay, the logics are inverted, okay, so we define for a given circuit the noise margin low and the noise margin high, okay. The noise margin low represents by how much I can exceed VOL without falling into trouble with the output remaining high, okay. And it is typically determined from the low gain region, from the transfer function from the low gain region. And once I hit the high gain region, I will be in trouble. My output will drop quickly. And this point at the intersection and the boundary of the low gain region is determined as the point VIL. فإذا my noise margin low هو VIL, V input low, which is the maximum input, the boundary of the low gain region. هلا بنحكي عن الديفينيشن لها. Okay. And so the noise margin is VIL minus VOL. And the noise margin high also, the noise margin high is really determined is limited by VOH and the lowest possible input before which I hit the high gain region, which we define as VIH. So the noise margin low لكن هو VIL minus VOL, and the noise margin high is equal to VOH minus VIH. And we typically design our circuit to achieve a large noise margin. يعني نحن we have to design our circuit so that I have a wide low gain region and a small but steep high gain region. Okay, so we have to determine the circuit parameters that guarantee this because the designer can only operate in those ranges. Okay, so those noise margins are defined like this. If I see how I determine VIL, I determine VIL and VIH from the points in the transfer function where dV out by dVin equals to minus 1. Okay, these are when the slope of dV out by dVin equal minus 1. These points represent the boundary of the low gain region with which I can operate, and they are function of the circuit elements. يعني they are functions of the transistor width, of K prime, of VT, and the resistor that I put and stuff like that. Okay, so these are done by design. For a specific design, I can find a specific set of points VIL and VIH. There's another point that we define on the transfer function, which we typically refer to as the switching threshold of the, I'll just take one more minute of your time, as the switching threshold of the inverter. اللي هي point that determines, that splits the domain into high outputs and low outputs, and it is the point at which Vin equals to Vout equals to Vm. We care for this point to be as close as VDD over 2 as possible because this means that my inverter has symmetric capabilities. It is as good in pull up as good in pull down. If it is not, if it is biased to one side,